In this video, we are going to see what is happening with a signal when it is traveling through a via, and you may be surprised how it looks. This video will help you to visualize what is happening in your PCBs, and it will help you to understand why and when ground vias or stitching vias are important and how to place them. This video is the second part of my call with Yuri, and if you like, you can watch just this video or also have a look at the previous one. In this video, Yuri is going to start with an example where a signal is routed on the top, then it travels through a via and continues on the bottom. The signal which is running through these tracks and vias during this simulation is a sinus signal. That's the reason why it will be flashing. You will see what I'm talking about. So we are ready to start. Here it is. Here is my call with Yuri.
Essentially, it shows where the energy of your signal propagates. So it's not in the currents, it's
Energy
in
fields.
Exactly, it's in the spaces.
Mm-hmm.
So your signal travels in the spaces, and in this case, it travels through multi-layer board. This is exactly stack up as you had it, and you can see that some of this energy,
Spreads
good view like this, it gets through, but some of them of it is spreading. What if you switch to 10 gigahertz? And you can see more energy spreading sideways. So you can see, and the boundary conditions here are infinite planes. So this is one of the specific Symbior features where it can simulate planes that basically goes to infinity. It's not a real board is limited in size, but it allows you to characterize how much energy you lose in the structure and possibly gain someplace else.
How do we know how much energy it loses?
That's a really good question. So for this we have metric or measure, localization measure, called dissipated power.
So basically, we are talking about the power which will disappear from going from the top to the bottom.
Exactly.
Okay.
We are talking about energies that lost from the signal. So some part of signal is reflected, so we don't account this energy. Some part of signal gets through, and some part of energy lost, dissipated, dissipated into heat, so warming up dielectric and conductor, and dissipating into kind of infinite planes. So it doesn't go back, or it appears somewhere. And it measured in watts here. With 1 watt signal excitation, we can see that the via without reference vias has steepest kind of increase of energy loss.
So the first one is a via with no stitching via.
Without stitching via. That's exactly what we observe here. So
and
essentially starting.
What is the X? Go back to the graph.
Okay.
So Y is the power and X was frequency.
It's a frequency. I simulated all the structures up to 120 gigahertz. Very kind of broadband sweep to see how they compare, like with 1, 2, 4, 6 stitching vias, and which case is the best.
And basically, when we have a look on the graph, this is basically also in some kind of percentage, because you said it is 1 watt. So if it's like 0.8,
1 watt. 1 watt.
Oh, 1 watt.
1 watt.
So basically 0.8, it means 80% was lost.
Exactly.
Okay.
80% of your power was lost.
So like for 50 gigahertz, almost nothing goes through. Just 1 via.
At 50 gigahertz here, 84, 85% of the energy lost. So, and 30 gigahertz, I have illustration for 30 gigahertz. And let me just switch back and show how it looks at 30 gigahertz, how bad it is. You can see that now you can probably realize where I'm getting to. So if you compare this, your energy gets through, and almost very small amount is dissipated. But then when you get to 30 gigahertz, well, half or maybe more in this case, energy of a signal is disappearing. So in reality, it may get back, but in form of with different phase and so on. So it's always distortion of the signal. So, and I have one cutout that shows clearly, essentially, some of the energy gets through. You can see arrows down. This is power flow density again, and most of it just gets sideways. Okay, escapes. So, well, we can take a look at what difference stitching vias.
Okay, I'm curious.
Just one.
Okay.
Like a new design. Okay. Let me just put this here. This one. Again, I use regular version of Symbior available at our website, Symbior 2022.02. And at via 1, with one via, at 1 gigahertz, we'll not see much difference. So the interplane capacitance and the energy is localized pretty much around the via. So at 10 gigahertz, you'll see some energy getting, and it's, to be more clear, you can see more energy getting this way than this way. So this via shield basically provides helping. So return currents going through this via, but on this side you don't have it. And again, at 30 gigahertz, it's not really helpful. So you can see that energy is spreading again.
So for higher frequencies, one via is not enough.
Again, if you switch to dissipated power, you can see one stitching via, this graph with circles. It has higher bandwidth if you can count, for instance, say, okay, 20% maybe my limit. So you get to 14 gigahertz, but not above. Above you'll start losing energy. In reality, this energy may appear somewhere, may get back. So planes are not infinite in real world. So there is not so much energy lost, but it will still lead to some distortion. The worst case is unpredictable distortion. So you always want your PC board designed and predictable in simulation. So you show that it works. So there are a few things that go into predictability is material models, geometry of manufactured PCB, and localization is one of the most important properties. So if you don't have this localization, your simulation becomes unpredictable. So
I would like to ask. So basically, if there are two vias, then in the second via you will again lose like 20% from the signal which left, correct?
Yes. You still have a relatively steep increase in the losses.
How does it work in the true Hall connector? So I know some...
Same thing. It's always kind of signal and how many stitching vias nearby. So essentially you are gauging the energy. And we can take a look at what difference makes two vias. You can see that curve is growing kind of much. You can get 30 gigahertz out of two vias, and then 4 and 6 pretty much identical. You can get up to 50 gigahertz here bandwidth.
So for very high speed, at least 4 stitching vias are kind of required.
Exactly. You have to always kind of consider what is the data rate and Nyquist frequency in this case, at least at Nyquist frequency, it has to be localized. Possibly above this, because of above the Nyquist frequency, there is substantial energy in spectrum. Let's take a look at 2. And again, it's just brief demo of where the signal is 10 gigahertz and 30 gigahertz. Okay, 30. At 30, it still radiates, and you can see from side view, you can see it radiates this way, where
the vias are now placed.
No vias, and at the vias, it's much smaller. So, and overall, it's much less energy dissipates at 30 gigahertz. To make it absolutely perfect, and you make them like this. So 30 gigahertz here, just immediately 30. And you can see at 30 gigahertz, same scale on the power flow density, and you have all energy getting
so much nicer.
Much nicer, yes. And let's just take a look at 70 gigahertz.
So this is 6 vias, correct? 6. 1, 2, 3, 4, 6. Yeah.
6, exactly. So at 70 gigahertz, it starts radiating up. But within the board, it's still kind of immune to everything. It doesn't radiate energy into this interplane space.
Can we find out? Can we find out how far we can place these stitching vias from the?
Absolutely. That's placement of stitching via is defined by your Nyquist frequency. So about quarter of wavelengths at Nyquist frequency is kind of what you need to be able to localize it. So in this case, if I put it way larger circle around the via hole, the localization frequency will go substantially down. So, and that's right here, I put them sufficiently to have in Symbior. I can open this right here. There is a via analyzer tool that essentially evaluates the localization frequency. This green line, single via, no stitching, we cannot really predict it above 3 gigahertz. So, and even to predict it up to 3 gigahertz, you have to simulate the whole board, like part of PDN, for instance, part of our delivery network.
So what is the purple and what is the blue line?
Purple is the impedance.
Oh, that's impedance, okay.
Blue line is the target impedance for this via.
Okay.
And green line is localization frequency. So if you put just one via, localization frequency goes up to 20-something gigahertz. That's purely based on electrical distance to this via. We put more vias, 2 vias, for instance.
And what is the localization frequency?
Localization frequency is where essentially your signal propagates predictably within the via structure.
So it means
basically gets through.
That's kind of your bandwidth or something.
Yes, essentially it's a bandwidth of your via. You can put it like this. This is the bandwidth of your via. 40 gigahertz, and then it basically 70 gigahertz with the 4 vias, and with 6 vias, same thing, about 65.
What is in the table? So show all layers, drill diameter 10 mils.
It's all parameters you may use to design via. It's the via design tool. In this via design tool, I may experiment with placement of stitching vias, for instance, and see how it affects bandwidth of the via and so on. So actually, if I switch to another solution,
wait.
okay,
So,
yeah,
just go back.
I go back.
So basically here you can tell, or you can set how far the stitching vias are from the hole, and it will show you the bandwidth which you can then. Okay, I understand.
Exactly. I can illustrate it like this. I can right here. It's a circle pattern. Diameter is 40 mil. What if I put them at the distance 140 mil? So my bandwidth way down. So it's below 20 gigahertz. So,
and before it was,
if
you put there 40 back, so before there was 70?
There was 40 mil diameter, and I increased it to 140
Yeah,
mil.
but when there was 40, then what was the bandwidth? 70? I don't remember.
It was quite a large bandwidth, 67.
Okay, 67.
But let's just put 140 and then reduce it to just one stitching via. Your bandwidth is down to 7.5 gigahertz. That's it.
Okay, I understand.
That's a tool to design via. You don't have to worry about the actually where the energy goes and so on. So as soon as you are within this localization frequency bandwidths, you are good with such via simulation. But this is, we call it pre-layout design. There is a post-layout analysis that essentially accelerates the whole process quite a bit. So electrical rule checking mode. This is part of Symbior Verify license. V-Analyzer is part of Symbior Verify license. This low cost $750 per year, not low. And this Symbior ERC and Symbior Fast SI mode, they are also part of Symbior Verify. So Symbior Verify allows quickly evaluate impedance of the vias, and you can see the via impedance here is and compare it with the target impedance, 50 ohm. And some vias here are blue, they go in 45. Some are red, it's single, and it also shows that it radiates. It radiates, and right here the data rate is 10 gigabit per second intentionally. So this via radiates, and naturally localization frequency is 3 gigahertz or below. So what if you put one V in the middle?
I have example. Oh, I have a question. So when you run ERC, then signal settings. These are the DRC rules. What you are checking if this circuit is going to pass. Yeah, signal settings. You set up. You would like to have 10 gigahertz. 10 gigabits.
Exactly.
Okay, I understand.
Exactly. And those just not simple rules, geometrical rules. It runs simulations. Every time it runs simulations for vias, it runs simulations for transmission line. So what we see here, this impedances, color-coded impedances, those are results of quick simulations. So it's, and we can see, we can enable just reference planes and see how the reference planes located here. So right here, Symbior didn't find this via in the middle for 10 gigabit per second. It's going to be via too remote to be found. So if you get to 1 gigabit per second,
there will be no error. Okay.
There will be no error. Exactly. So this via is relevant to this one. Those vias become green, so they at such low frequencies they are not obstacle anymore. So they're closer to target impedance. So impedance continuity not violated. So we don't have violations here. So if you switch to one via located here, again, I simply click and run. This is production version of Symbior. And switch to 3D. You can see the V is still red. It's again, this is for 10 gigabit per second again. Those are blue. So how to make them different. Well, first thing I can back drill. I can back drill some of them. Like this one is back drill. Then it's better. So no via stuff. Green. But those I need to tune to have them.
So we would like to, for example, move the stitching via a little bit further or closer from to achieve the proper impedance.
Well, stitching via, let's just experiment with this. So I switch to fast signal integrity analysis. Again, it's part of our Symbior Verify license. I build the model, extract it, and simulate. This is just live part of this schema. It's a pulse response, and we can see substantial reflection over here. Return loss is quite high. Insertion loss like this. So what is the problem? The problem are vias, via holes. And Symbior extracted those via holes as we saw as parameterized objects. Okay, it was project 2.
So we will change the impedance by, I remember now, I think changing the paths or opening and the hole size, I think, yeah.
Exactly. You're right. So we go to this schematic and edit this multi-via. We call them multi-via because of those things. The via, single via doesn't exist. From the signal integrity point of view, it's always a combination of vias. We call them multi-via. So there is a white trace on top. The via impedance goes up here, as we saw this red dot. So what do we do? And the bandwidth is sufficient for 10 gigabit per second. So 10 gigahertz here, green line. So what do we do? In this case, we can increase via diameter, like use wider, and that's basically reduces.
Wow.
Exactly, and well, and maybe reduce a little bit antipaths to have more capacitance. So we go to this is antipaths. So they are 50 mil. So we can reduce to 40 mil, for instance. That's it.
Cool.
We're basically close to target impedance. And with the other via, so one of the vias was not, this one was also blue one. And in blue one, we have the opposite kind of case. The impedance goes sharply down.
Too low.
So right here, we can reduce the drill diameter to 20. Maybe that's too much. 30. That's about right. That's it. But the bandwidth here is barely above 5 gigahertz. So what do? We move stitching via closer. So right here, stitching via is located at
100 mil.
100 mil, yes. And if we put it at like 80 mil, the pad, also size of the pad, we
it's
need
too big.
to reduce it a little bit. It's pad diameter. It's okay. Now, if you take a look at the circuit again, so in this return loss, for instance, it just runs analysis. And I run analysis. Now the return loss goes way down. So from one side it's still high, from another side it's low. Pulse response is much cleaner. So you can see that,
no reflections.
Exactly, we've got rid of the reflection. And technically we can take a look at TDR, for instance, of this. So switch to Gaussian step, for instance, and switch graph to TDR plot. impedance, and let me just adjust it here to coefficient 1 impedance. So this is the impedance. So it looks a little bit weird, but
yeah,
that's the V in the middle. You're exactly right. And on this side, we still have kind of capacitive. So that's a practical kind of part. Well, technically, we can just go through this case.
Yeah? Can we go back to the one of the graphs which was showing the not this one, the other one?
False.
The first one. Yes, the first. Yes, this one. So this one is.
This is return losses. They are way better than they used to be. So below -20 up to 10 gigahertz. So we improved.
Oh, I think before there was -10 or something like that.
Yeah, it was very quickly to -10. So we can.
Return losses. It means how much will go back, or how much.
Returns to the transmitter.
And ideally, we don't want to have any return losses.
Yeah, we want them to as low as possible. So the ideal channel is constant impedance channel with a target equal to target impedance, and the reflection is 0. In dB is -infinity. So essentially, that's a best case. So when we optimize the channel, usually it's focused on what is trace impedance and so on. And I actually started some up notes on this subject, like impedance and reflections right here. Reflections from discontinuity. So it focuses specifically on the return losses, like how to mitigate them, and what is the power of the signal, what are the components. Like you saw this power in minus power absorbed, reflected, leaked, coupled, and today we observe this leaked power, which we use for as a metric or measure for localization quality. So the less power leaked, the better the localization of the VIA.
Okay, we can go back. We can go back.
Yeah, and after this, after you ensure the localization, you have to also ensure the impedance, continuity of impedance. So, for instance, in this.
So now we applied the changes to our board, and we are going to run this simulation.
Unfortunately, no. We cannot really kind of bring it back. So now you have this improved multi-via.
Okay, so I'm going to interrupt you again. So basically, once you do these calculations and simulations, then you need to go back to your board and make the adjustments, and then import the board, and then simulate it again, and everything should be then much better.
Exactly, and then you bring it back here and run the analysis and run quickly. Like, okay, for instance, if you improve this. We run the analysis. Right here, it's same via, but with only a larger number of stitching vias.
Okay, so this is another example. This is another example.
Yes.
We have 6 vias around, 6 stitching vias around the via which is changing the layers, and we are going to have a look at the results. Yeah.
And the result is still the same. So it's the via has too high impedance. So in this case, if you zoom in, about 63 ohm input impedance. So and if you want to improve it, you can extract it, improve it, and then you go to layout to Altium, for instance, where you created this board and make adjustment. It's inconvenient. I agree. It's much better to have some kind of 2 ways.
No, it's okay. It's okay. You have to make the changes in your design anyway, because.
Yeah. So somehow you have to get it into manufacturing,
yeah,
right?
Exactly.
And get your board manufactured and have properties exactly as you simulated. So the two properties, two things are really important to have this predictability. Is first, materials and geometry. They are correct, and another one is localization. So we I also wanted to show.
I have another question. Sorry for keeping interrupting you. So do you remember what was the impedance of this connection before of the via? It was now it is 43.7 ohm, correct?
No, it's we need to zoom in to see the
okay,
via,
63. Okay,
63. So on this design with one via we used. It's still switched port view. It's still kind of same thing.
Okay, because I'm just curious if a number of vias is okay. So number of vias will not really influence the.
It does influence. There is a capacitance from vias and inductance changes, but it's not so much as antipod drill diameter. Drill diameter has a big impact on the impedance and antipods. If you place stitching vias very close, then they'll matter a lot. In designs where people design transitions for connectors, so vias up to 70 gigahertz, stitching vias are really close, and they are a major part of the impedance. So little movements of stitching vias change the impedance a lot. But right here, this via is
far away.
Kind of relatively far, and small drill diameter makes it really kind of. That's what makes it inductive, actually. The whole structure is thin or small drill diameter, I would say.
Okay, you can continue.
Yeah. So I expected a question from you that what about the differential? So if you switch to differential,
but you wanted to say something about the 6 vias, or no? You didn't want to say something about the 6 vias? When I interrupted you, you were starting about differential.
Yes, exactly.
Okay,
exactly.
Okay. So let's talk about this differential signal.
So you may think that switching to differential, you may forget about stitching vias. So let me show you a simple example. That's what we are now looking at, the true differential. And presumably they should be fine without any kind of stitching here. But if you go take a look at this at like 1 gigahertz and take a look at 10 gigahertz, you'll start seeing some energy disappearing mostly sideways, this way and this way. And 30 gigahertz, you can see more and more energies going sideways.
So this is basically exactly the same as if we are talking about single-ended and stitching via. That's exactly what is also happening here. It's kind of same.
Right here, currents are in opposite direction. So they basically have to compensate each other, right? So the one current becomes the return current of the other. So if we let's just visualize the currents here, compute field views at 30 gigahertz, current density, surface. This is excitation plus minus 1, and not instantaneous. Let me try this. Okay. So essentially, that's and actually I needed the arrows, and now I need to switch back arrows. Okay. If you take a look at the surface of the vias, the currents are going in opposite direction on this surface, up and down, up and down. So basically, they're compensating each other. And but it still creates radiation. See? And the
Okay,
reason
I
is
know
really simple.
what you would like to say. I remember now, because they should kind of cancel each, or we would expect they would cancel each other, but that's not really like 100% cancellation.
Yes, it's not 100% cancellation, and if you model a phase array or two currents in opposite direction, just at some frequency, if you take a look at the radiation pattern, they will not radiate perpendicular to the location, but they radiate sideways. So, and right here, what you see, the Vs are radiating sideways, 30 gigahertz.
So they really like kind of cancel each other in the middle, but not on the sides.
So they're not radiating this way, they're radiating sideways. So now you know where to put the stitching Vs. So if you put stitching Vs kind of, let's just put two stitching Vs like this, will it help?
No.
And we'll see. Again, 30 gigahertz. And side view, you can see radiation this way, and even in this way. So it's visual, but there is a kind of proper metric for this that we looked at. And again, if you use cut plane, you can see they still radiating sideways. So basically, putting stitching Vs like this is not a good idea. So I saw some kind of expert recommended like this and so on. But what if you put it like this? Again, this is 30 gigahertz. So immediately jump into 30 gigahertz. With differential Vs, we obviously have much higher bandwidths, even without stitching Vs. It's still kind of functional at much higher frequencies comparing to single, but they still have the problem. So right here, we see that those Vs preventing the radiation. You can clearly see it. It's still happening. They're still kind of reflecting. This is power flow density. And if you look at the formal measure for this, and this is a formal measure. Again, it's dissipated power with 1 watt excitation differential. And you can see even without stitching Vs, this one is without stitching zero, right? We have like 15 gigahertz bandwidths, or even more if we measure 20%. Okay. 20%, it's 24 gigahertz. So if you put two stitching Vs, just one stitching Vs, it barely improved. If you put two stitching Vs, but in wrong way, like not on the sides of the differential V, but rather
between the tracks.
Between the tracks, for instance, and so there are some recommendations on this. We cannot deliver. It improves a little bit, but not much. And only when we put two Vs on the proper sides, we have substantial kind of increase in the bandwidth and substantial decrease in the dissipated power, in the power lost.
So there is actually big difference between using single-ended and differential pairs. They work
absolutely.
A little bit. The technology
we can
is different.
Compare. Yeah. You can see here, you got this mess here. Exactly. And you can see this one. This is big improvement. So you basically up to 10, 15 gigahertz, you'll not have any problems if you don't even put stitching Vs. Unless you care about the common mode. Differential mode is where currents go in opposite direction, but in common mode they go together. If you take a look at the dissipation of the common mode for differential, it looks almost identical to single-ended. And here, it doesn't matter where you put those stitching Vs. You can put them on the side or where the traces are. It still confines the common mode.
So this will happen if you don't do the phase matching? If the edges are not traveling
in any link, you have kind of, ideally you launch the differential mode, right? But then if you have turn left, turn right, you have to introduce some compensation structures. You have some energy transformed from differential to common mode. And to have it predictable as differential mode or simulatable and have effect of the common mode on the final signal, and there is a kind of measure for this differential to common mode crosstalk, we call it. You have to predict behavior of every single structure on the way. That includes differential vias. So if differential via without stitching vias is well predictable up to 10-15 gigahertz in this case, so with this location, with this distance between vias. For common mode, we have the same problem that if you don't put stitching vias, it becomes unpredictable. It loses energy. What does it mean unpredictable? You won't be able to predict common to differential noise or crosstalk, sometimes called. Common to differential noise you won't be able to predict, and this is unknown that you end up with in your design. If you are lower data rate, below 10 gigabit per second, those mode conversion effects do not matter much, but when you get to like 30, 50, 100, or 224 gigabit per second, then everything this matters. So small amount of crosstalk may kill your signal with the amount of losses you can encounter during the way in the link.
So basically, I think we should explain a little bit more. So as you said, if there are, for example, if we would only have like 2 straight differential pair lines, then that would be perfect. But because of all the bending and all the phase adjustments and everything, there may be some common mode difference between these two negative and positive signals, and that's still something what can make problems if we don't use the stitching vias in lower frequencies.
Exactly. If you use stitching vias, rephrasing it a little bit, if you use stitching vias, we will be able to predict the effect of those transformations.
I understand.
And anticipate it and make like routing slightly different or pay more attention to this differential to common mode transformation. So reduce it. Or we can get along with what we get, but in case if you cannot predict it, so you'll not be able to predict the effect of this differential to common transformation, and you end up with uncertainties in your design. That's it. That's really bad idea. So essentially everything has to be localized, including the common mode in a good design, high frequency or high data rate design. You have to think about it as Ralph Morrison, that everything you're dealing with guiding structures, right? And signals travel in spaces. As soon as you reduce this space and don't get anything in this space, you're fine. And in differential line, signal travels in this wave guiding structure as differential and common mode, or as even and odd mode, let's say, be more precise. So even mode or common mode is undesirable, but you'll have it if you turn traces, and inevitably you have to go through some turns and so on, and you'll get some transformations, and then you have to predict those. And, it's better to have localized both differential and common. Differential is very well localized or self-localized, I would say, up to some frequencies, as you can see.
Okay.
Then it may start radiating sideways, or not radiating, but be dependent on the structures that essentially located nearby. So again, this modeling is a kind of as a model, it's there are some assumptions, right? And we cannot afford really simulating of the whole board to predict some effects.
So basically, if we would go back to the simulation with the arrows, then basically if we, in the ideal world, if there is only this differential mode, then there will be always the opposite arrows and always basically the same size arrows. But because there is this common mode, then there may be situations when, for example, the arrows in both vias will be same direction, for example, or they will not have same values, and that's when these stitching vias will become more critical.
Yes,
okay.
Yes, that's correct, and that's essentially what we see here on this current density flow on those barrels. I needed to simulate it at low frequency probably to
this is interesting because you know, if we go to this first example where we only have the ground via and single-ended signal going through from the top to the bottom, then also in this case basically you have currents flowing one way and also the other way, correct?
Well, let's take a look.
Okay.
If we compute current flow density here, let's just say for...
But put there the via. Put there the via. Okay. Yeah, we need
no stitching vias.
Okay.
Where the current returns? The question. Well, let's just take a look at 10 gigahertz current density surface. Hope that this time it will work without problem.
It will go away, I know, but if there is the ground via, then how it looks when there is one stitching via?
Yeah, we will look at this as well.
Okay.
So right here you can see those currents. Basically, that's why I'm saying that currents is not really
important.
They return. So you can see that there is no current on the via that does not return. They all return, but they return through two things: currents in the planes and currents between the planes, displacement current.
Yes.
So if we compute displacement current here, we'll see where actually it goes, like displacement current and volume, and we'll see displacement current here. Please just switch to logarithmic scale to exaggerate it a little bit. This is displacement currents. That's where return current goes. You see? It's all over the place. It goes everywhere.
Okay.
So, and if you switch to one via and compute the currents over here, essentially we're repeating this experiment that we did on the big piece of board. And again,
I'm curious now.
10 gigahertz current density surface. Switch to...
We need to use arrows again,
Yeah, I don't know. Actually, okay. This is the return current. And it's better probably visible on color view. Let me just switch to color here. And you can see, yeah, that's better. So arrows are not visible, but you can see that vias are, the stitching via nearby is getting some colors of the current, and the current here in dB.
But what direction the currents are flowing?
The direction? Let's just
I would like to
take a look at the direction. The directions, you can see they, let's just take a look
they
at
are opposite.
Side view.
Yeah, they are opposite.
Yeah, they're opposite. Yeah.
So now the question is, why differential pair is different even if here they are opposite.
The differential via is does not have this transition. So right here you get this. You can see on the top layer here some redistribution of current. So some currents have to go through this source into the stitching via. There is a redistribution of current on the top here, and that's one thing. Another thing, it's differential case that looks almost like a transmission line. That always makes it the structure much more impedance control, I would say. So it's maybe not right word, but you can. There is still kind of capacitive loading right here, right here, right here. So some capacitance to the planes. But overall, if you
it's more controlled environment, I guess.
Exactly. If you remove the planes completely, it will still work as a transmission line in differential mode. So in case of this via.
This via is not only the via, but it's basically also all the planes which are connecting the via. That's the problem.
All the planes, and it has to the current has to be redistributed at every location. And technically, and this structure has much smaller bandwidth. Again, if you compare the dissipated power for single-ended, again, this one is with one stitching via. So what at 0.2 or 20% loss, we have 14 gigahertz bandwidth. What about the differential without stitching vias? Just take a look. Differential without stitching vias 0.2. We have at 24 gigahertz. You see, that's a measure that not only visual but allows to distinguish or define the bandwidth and more formally kind of compare. Technically, yes, you're absolutely correct. That the single-ended with one stitching works the same way. So the major return current, part of the return current, is on the stitching via. So I actually did right here logarithmic scale. What if we switch to just not logarithmic but linear scale? Yes, and you'll see linear scale is barely visible, but you can still see maybe not. Maybe we can increase the size of those arrows to be able to see them better. So you can see that where the current goes on the stitching via, it goes on one side of the stitching via. So it's in the model. You can see those larger currents.
So it's basically the side which is close to to the via.
Close to the on the other side, you don't see currents at all. So if we again color map it, you can see it like this. So that's where the mass of the current is flowing through the side of the stitching via. And that's. It's always a good idea to have stitching vias nearby that provides the bandwidth we need. But differential is maybe better, even better.
Wow.
I can see designs now both in differential area and in single-end. Single-end provides more space, and if you have some kind of micro manufacturing technology, you can basically localize it quite well and get through without any problems. So save space.
Perfect. So these are all the examples which you prepared?
Yes. And we are already experimenting with this kind of.
Wow. Yuriy, this was super useful. This was like really cool. Now I know what was happening in my simulation, what I was doing before.
Okay, thank you, Robert, and thank you for your time. That was very fun presentation.
Thank you very much for
for
preparing
me.
all these examples, because yeah, it had to take you some time to prepare everything.
Okay, and anyone who was watching can download the pricing view.
Where do you have price? You have pricing on your website?
Oh yeah, on our website, if you go to price and order form, log in, you can download it, but if you log in, you'll see the pricing. Symbior Verify, this is Symbior Verify license. If you click on configuration matrix, you can see what is included in Symbior Verify. So everything except 3D EM solvers. Essentially, 3D EM solvers are not
3D EM field solvers are these 3D animations?
Yes, that was used in the animation. That included only in Symbior Explorer and Symbior Complete. Symbior Explorer is for pre-layout design of views up to very high frequency, up to for frequency above 10 gigahertz basically position.
Go back to the price list. I would like to see the prices there.
Price list, Symbior, this is Symbior Explorer, pre-layout with 3DML solver. So prices 1 year license start from 2,500. Then Symbior Verify, it's a post layout without 3D electromagnetic models. This ERC mode and fast SI modes that we used in demo.
For what we were doing today, what licenses you would need?
With what we were doing in this running ERC and fast SI here, you need Symbior Verify.
Okay.
Even VIA design, Symbior Verify.
And for the
post
VIAs?
layout analysis, yes. But if you want, if you need those 3D models for you, and you need them only if you go above like 10 gigabit per second data rate, then you need 3D electromagnetic models. You can still run ERC mode to evaluate the kind of impedance continuity, reference integrity, including VS and crosstalk. That we can talk separately on the crosstalk. So that's and then those are prices for Symbior Complete. With an extended frequency range, we position it like this.
Symbior Complete, it means it includes Verify and Explore and
everything.
Okay,
everything.
So basically $3,000 and you can do everything.
Yeah, it's a 3 months modlock license.
Okay.
Around 3,000, yes.
Okay, perfect.
So
and if people would like to buy it, or if they have any questions, they can contact directly you, or you have something on your website?
Yeah, absolutely. Or place an order on our website. And get the license. So try it first.
Okay.
See how it goes with their designs. Last time I showed you how it works on very complicated designs. So it's not like restricted capability to just simple test board like this.
Yeah, of course.
Scalable, very scalable.
But I think from this demonstration, people will get the idea what they can actually see and what they can explore, because I think these simulations are super useful, not only for like these ERC or DRC checks, but also to understand what is happening on your board and kind of prevent all these problems what you can have if you don't understand what or how you should properly place components and vias and tracks and how to route them, how to do stack up, because suddenly you understand what is happening there and it will help you to, I think, do a better job.
It will guide you through. In this ERC mode, it shows you some tips also. It creates reports, I didn't show it. Create reports where it guides you through what have to be done to fix the problem. And the whole idea of ERC is to guide you in the direction of design of predictable PCBs. So that's important. So it indicates all the kind of potential problem in predictability, potential problem in signal integrity or EMI-MC. So and unpredictability or loss of localization is a major thing. That's what we essentially try to show in this demo, that for practical reasons you don't have to simulate all those fields to
I'm sure you don't have to, yeah. But as I just explained, like, it's very important to understand it, and that's
very important to understand. Yeah. Yes, that's where your signal travels, essentially.
Exactly. So
not on traces.
Thank you so much, Yuriy, for this.
Thank you, Robert.
And that's everything for this video. What do you think about what we have just seen? Leave comments. If you like this video, don't forget press the like button. If you would like to support this channel, it helps a lot if you subscribe. Thank you very much for watching and see you next time. Bye.